Let's go on with basic and applied physiology, talking about the membrane potential. We've known potential difference. Potential difference is simply the voltage between 2 points. So when you're talking about membrane potential, we're simply talking about the voltage across the cell membrane. So the cell membrane divides the inside of the cell from the outside of the cell. Inside of the cell, the major ions that we have got potassium. Let me just say those which have got a P: potassium, phosphates, proteins. Those are the major ions inside of the cell. We are also going to include magnesium. Outside the cell, the major ions we have got sodium, we have got chloride ions, we also have bicarbonate ions. These are the major ones. Just something quickly that we should be able to know is that proteins are made inside the cell in the process of translation, and so expect them to be much higher inside the cell, just like amino acids, because these are the ones which make up protein, so they are much higher inside the cell. Glucose, on the other hand, is much higher outside the cell. So, because of these ions which are inside the cell and outside the cell, we're going to find that there's going to be different distribution of charges inside and outside of the cell. Inside of the cell, we are going to have more negative charges than on the outside. So, the outside is more positive than the inside. So, because of that difference in charges, when charges begin to move like that, that is electricity, right? So, electricity is going to be formed. In other words, there's going to be voltage because of these charges which are inside the cell and outside the cell. Why? Because outside we have got a different charge, which is positive. Inside we have got a different charge, which is negative. And charges are able to move like that, and that is going to give us voltage. All right. So the study of the movement of ions across the plasma membrane is referred to as neurophysiology. So the movement of ions from the outside of the cell to the inside, from extracellular fluid to the intracellular fluid, is known as the influx, and the other way around, from inside to the outside, is referred to as efflux. So movement of ions across the cell membrane is not only depending on ion concentration. We know that movement of substances move from the region of higher concentration to a region of lower concentration. But for ions across the cell membrane, it does not just depend on concentration. You can have a lot of sodium outside the cell, but sodium will not be able to move from the outside of the cell to the inside of the cell. Why? Because we're also talking about charge. Because sodium is positive, we also have positive charges inside the cell. So you don't want more positive things to be moving outside the cell going into the inside of the cell, because you're going to be increasing positivity. So if positivity as balanced, or let me just say charge as balanced inside and outside the cell, even if the concentration is different, there's not going to be movement. So ions will no longer move if the charge inside the cell and outside the cell is equal. Though not necessarily that ions are going to stop moving, because when we say ions will no longer move, we necessarily do not mean that they will just stop moving. This just means that the number of, let's say if we're talking about sodium, the number of sodium ions going inside the cell is equal to the number of sodium ions going out of the cell. So they are canceling each other. The net movement is zero. That is why we are saying no movement. But there is actually movement that is getting to happen. Okay. So the ions which are going in and the ions which are coming out, they are basically equal. So this is what we refer to as equilibrium potential. So what is equilibrium potential? Equilibrium potential is simply the equilibrium that is reached when the number of ions going inside the cell and the number of ions coming out of the cell are equal. In other words, the influx and efflux of ions is equal. Right. So the movement of ions across the plasma membrane generates an electrical potential. When ions get to move across the plasma membrane, there's going to be voltage being produced. So increase in positivity, a positive charge in the ICF is known as depolarization. Now we know that when we are talking about the ICF and the ECF, Inside the cell, we are calling that as ICF, and we have got more negative charges. Outside, we have got more positive charges. So when positive charges are moving from the outside where there are a lot, down the concentration gradient to the inside where there are few. Let me talk of sodium. Sodium is more outside the cell. It is less inside the cell. So when it starts moving from outside of the cell to the inside of the cell, because inside the cell, remember, I've got negative charges, right? So to negative charges, when you start adding positive things, the negativity is going to reduce. Let's say we have got negative 7 and then you add positive 2, you are going to get negative 5. So the charge has done what? It has reduced. So that is why we are saying depolarization. We are reducing the polarity of the cell. Polarization. What is hyperpolarization? Hyperpolarization is simply the increase of negative charge. So let's say we have got more negative charge that is entering into the cell. That is going to be called hyperpolarization. Or the negative charge inside the cell is increasing. Okay, that is hyperpolarization. But if the positivity is increasing inside the cell, that is depolarization. Now, if you were, let's say you are having a negative 70 charge inside the cell, and then it went to negative 50. That is it, depolarization. Why? Because the charge moved from a more negative number to a less negative number. So for me to return back to negative 70, that is going to be called repolarization. Now, instead of me going to negative 70, I go to negative 80. That is going to be called hyperpolarization because I've gone beyond the normal polarity. Right. So to calculate the equilibrium potential of an ion across a plasma membrane, the next equation is used. And this is the next equation. Positive or negative 61 millivolts multiplied by the log of the concentration of ions outside the cell divided by the concentration of ions inside the cell. Now, this I shouldn't even have said positive or negative. It's supposed to be positive when we are saying out over in. So if I put in on top and then I put out down, then I'm supposed to put a negative here because I've reversed the log. So the voltage is measured in millivolts because if it is in volts, that can kill the body. That is too much for the body. So this formula which you're able to see is only used at normal body temperature, which is 37 degrees Celsius. But if the temperature is different, then we are going to use this one. So to calculate the plasma potential or the equilibrium potential, it is going to be the universal gas constant times temperature divided by the ion constant multiplied by Faraday's constant natural log of concentration outside the cell divided by concentration inside the cell. All right. So just what I explained, this is what we're able to see here. So if we have got, let's say, inside the cell the charge is negative 65, I start reducing the concentration. I start reducing. Now, I mean the charge. Now, if I'm going up, of course, it's not reducing, right? Because I'm increasing. See, we have got negative 65, we're going to negative 55. Negative 55 is bigger than negative 65. So what are we doing? We are depolarizing the cell. When we reach the top, we start coming down. That is it, repolarizing. But if I exceed, instead of me just reaching at negative 65, I was at, I go down. That is hyperpolarization. And then one, I'll come back to the normal state, and that is called the resting membrane potential because the cell is at rest. Let's have this example. Calculate the equilibrium potential of sodium and potassium given the concentration of sodium outside this and inside the cell as 141 milliequivalent per liter and 14 milliequivalent per liter. And that of potassium is 4 milliequivalent per liter and 140 milliequivalent per liter, respectively. So, respectively, we are mentioning outside and then inside, meaning that the first value is mentioned at the outside. So, to calculate the the membrane potential, it is 61 times log of concentration out over log of concentration in, and so that is going to be 61 times log. For sodium, the concentration out is 141, in is 14. So this is going to give us one. I'm going to get a positive. Why? Because I started with out over in. But if I start with in over out, we can see I'm going to attach a negative here. And let's calculate for potassium. So for potassium, it's going to be negative 61 log. The inside the cell is 140, outside the cell is 4. This is going to give us negative 94 millivolts. So that is the unit of membrane potential, not in volts but millivolts. So because potassium, sodium, and chloride ions are the most common ions that get to pass across the cell membrane, or they are most abundant ions in the cell membrane, we need to know their membrane potentials. So for sodium, it's about 61 millivolts. Potassium is about negative 94 millivolts, and then chloride is about negative 89 millivolts. So these are the membrane potentials of